Great. It's good to see folks again here. I'm going to be leading you through having achieved a lot of progress already, I'm going to be leading you through a set of additional topics today, which are going to fill out much of the knowledge that we've been building up. I'm hoping to hit today aspects that we prioritized yesterday, coverage of implementation intervention, aspects of calibration, health economics models, use of database and other mechanisms for recording data and outputting that data, and a little bit on bringing data in from data sources of different sorts as well. We're also going to be discussing calibration as a technique and the use of particle filtering, which I consider, when used together with dynamic modeling, to be a extraordinarily powerful addition to the dynamic modeling toolbox. I wanted to begin, as I often do, with a retrospective on yesterday's learning. Yesterday we actually covered a set of material. This involved an introduction to AnyLogic's GIS features, the first building of a hybrid model, a little bit on the intervention front, but more on the discrete event simulation front, and some further extensions using messages that govern agent interactions with each other and with the environment. We'll be continuing on some of those items today, but I wanted to reflect on others that won't be the focus today, but are important features in this environment. So both that initial model with which we started, the GIS model, the model that we opened the very first day that had supermarkets and convenience stores and people seeking food from those, that was situated in a GIS context. And we yesterday adapted this pre-existing model that we had for a GIS context. Now, when one combines GIS data with a dynamic model, it's often in many forms. It takes different forms. And in a given model, it may tap different features of using that GIS data. In some models, what we're seeking is to use GIS data to inform the placement of resources in the model. We saw that yesterday, where we placed clinics according to some empirically identified locations, right? We searched for clinics within a defined region. We placed those clinics there. We also made use of another feature which had to do with the kind of the region boundaries and so on, different jurisdictions that we could tap into. We could place resources within those jurisdictions using mechanisms. We had this random point inside mechanism where we placed houses within random points within the city of Sydney. Beyond that, we were also behind the scenes making use of some GIS data that in a way that wouldn't have been that obvious perhaps. And I want to draw your attention to two components. If we go to person in this model, and we go over here to the care-seeking state chart, you may remember that when an individual first seeks care, that individual finds the nearest clinic to themselves. Do you remember that? No? Here, what's going on is that we're identifying a clinic from a set of all clinics in the model that lies nearest. And this get nearest agent mechanism exists in several forms. We can ask, as the crow flies geographically, what's the nearest agent? We can also ask, what's the nearest agent by a route? Okay? We can ask, for example, according to roads and the fact that you have to drive in a certain way, what's the nearest agent to ourselves within this space, from within this collection? So here we had a person, and they were seeking the nearest agent from the set of all clinics. And we could ask this with a route calculation, in which case the distance is calculated via a route provider, or we could do so in a way that simply use the geographic distance, as they say, as the crow flies. So this too was something that could use geographic information. We, at the very least, were using the geographic positions and latitudes and longitudes of the different resources and people. Another way was actually indicated on the next line here. When we moved this individual to a location, we did so with via routes that are present in the space. So I noted yesterday, if we went to down Main, and we select this area here, we could go and look at preferences within this area. You notice in this routing thing here we're delineating through what type of channel, what sort of route we want people to be routed. We want people to be directed. And I understand, although I've not conducted it myself, I understand that in a given model, simultaneously, you could have some individuals who might be routed via a car network and others via a bike network. So if we were interested in active transport, for example, and we wanted choice of modality for travel to be something that was decided on a per individual basis, we could do that in the same model. So we'd have, in one case, an individual considered car routes, in another case, foot routes or bike routes. And the mechanism that actually set them into motion, that actually got them going, was in fact the mechanism we just looked at, although I've now closed that, but here with this move to. Now, the features of this were considerably more obvious in that very first model we looked at, because that had food-seeking behavior over the span of days being captured. If one were to look at this model here, we'll go down and I'll run it with a small population, 100 without behavioral counseling. Here, we're going to have this small population, and when I run it, you'll notice that down here in the running, there's this little downwards arrows. Do you see that? I don't know if you can make that out. That these little blue facing downwards arrows. Yeah. Those blue downwards arrows are indicative that there's. Oh, look at that. Oh. Okay. We'll come back to what's going on there in just a second. That was an elaboration that we didn't have before. So these blue downwards arrows are indicative of network access. It's trying to contact the route provider. Now you notice that they've disappeared. This was reflecting the fact that for the first little bit, it needed to figure out the routes between agent homes, the homes of those agents, and the facilities to which they're traveling. And once it figured those out from the limited number of homes, it could use those to direct them on an ongoing basis without needing to go back to the server. So often here, in terms of performance of the model, you take a real hit early on, and you then have a much faster model as time goes on. I'll draw your attention to one thing here. So this population, 100 with no behavioral counseling, if we looked at its associated assumptions, and I particularly want to draw your attention over here to the assumptions involving random numbers. Here we're having a random seed. What that means is if I run this model twice, run it again, it will be once again accessing that network, and we'll have to figure out for this set of individuals or this set of locations associated with homes, what are the routes to these particular resources, these medical clinics. So that is a hit you'll want to be aware of in any logic. It's one that has a very material impact early on, but after that it turns into a much more minor thing. Now, if we were to slow this down, we might be lucky enough here to see an individual move. But because the time frame of the model is such, we'll be unlikely to see the move in too much detail. You could see them quickly sort of flash across the space between themselves. Here, there is a model like this, there's very limited gain. A model with this sort of time frame, very little gain by actually having them visually take the route. It may be quite relevant in terms of decision making, which clinic they go to, and it's probably not as deterministic as we let on that they always go to the nearest clinic. But the point is that actually having them move in that sort of way in a very detailed fashion along the route, given the time scale of the model, it doesn't seem to make much sense. It's a level of detail that's both unlikely to be germane to what we're trying to capture dynamics-wise, and number two, it's unlikely to be meaningful to stakeholders because they barely see it. In those cases, we are advised to, instead of using move to in that way, we can use another mechanism that we didn't cover but bears emphasis. We can say jump to, okay? Jump to. And here, if you engage in jump to behavior, it won't actually bother moving you along the route. It will just jump there, more or less immediately. And for a lot of models, that's sufficient. You actually don't need them to move, but you might want them to make decisions based on the route, and for that, you're going to be using routing information. Okay. So that's another aspect of the geographic context. Another aspect of the geographic resources or use of geographic information consists, ladies and gentlemen, of the fact that we will in some cases seek to accumulate information on the map as with regards to resources or draw on information. So, for example, air quality readings. We might know they're worse in some areas of Sydney than others, and we might use that information from a database. Or, in some models, we may wish to accumulate information from the agents to the surrounding environment. In these cases, what we will sometimes do is divide the space up into a set of squares and accumulate that information there. There's a model in AnyLogic's example models that's a fairly visually evocative model. It's an older model, and it's one that I find its implementation unfortunate. It's called Wandering Elephants, and I object at a software engineering level to a lot of the way it's been implemented, But the basic gist of it is that it illustrates this idea of having resources that are geographically gridded, and here elephants engaging in foraging and water-seeking behavior in this context. When an elephant becomes thirsty, it turns red and approaches a water source. The elephants here are engaged in foraging, moreover, which is eating away vegetation, which is maintained for each grid cell. And although the impacts of that on the vegetation are non-obvious, if we speed it up here, you'll see them kind of chipping away at this vegetation over time. And if the number of elephants is decreased, the vegetation will actually grow back. Okay, so there's some dynamics associated with sort of replenishment, etc. This is actually this model originated before AnyLogic featured pronounced GIS features. We were among the first, certainly I think the first users in health who tapped into geographic information many years ago, and AnyLogic has come a long way since then. But this even predated that work, and this is conducted in a way that, from a geographic perspective, is not fully, it's not integrated with GIS data per se. But the idea is that each of these the squares here is described by a so-called array, a two-dimensional array, and we keep track of the amount of vegetation in one array and the altitude in another. So when it comes to geographic models, this notion of kind of having resources or having accumulation effects that are geographic specific is an important one. I would draw your attention along those lines to a few other models that we have posted and shared. So if you go to here, tiny URL, to the Feb 2017 materials, you will find in the example models here, there's a set which are present in the hybrid modeling area. That's its own subfolder. Hybrid modeling area, which illustrates some basic features here. Some of these we're going to come back to later. For example, this basic health economics model. Some illustrate features we saw yesterday, like this multi-clinic model, where people seek care in clinics that are spatially situated. And some we've gone through already, like this GIS food environment. But I'd like to highlight a few here. One is there's a gridded system dynamics model here, where basically we have a model of dynamics among grid squares, each of whose grid square is characterized using a system dynamics model, and then there's some interaction between neighboring squares. These sorts of models are fairly common in ecology. Okay, so I've just downloaded that gridded hybrid model here. I'll open it up, and this gridded hybrid model has each patch characterized according to a set of mechanisms. This was somewhat inspired by discussions of sea lice, which one of my boot camps participants, actually several of my boot camps participants, were rather interested in sea lice. And we had immature and mature sea lice. They mature, there's a patched population, and there's some endogenous dynamics of birth and death, but then there's also migration from nearby areas. And the point is that this is situated in space within patches, and each of these patches exist within a broader context of a grid. And so here we have these patches, each of whom undergoes dynamics. You could see them changing over time here. according to these underlying mechanisms, and by interacting with the model, we could cause a proliferation of sea lice in that area and kind of see, or these organisms described here, and see how they spread to other areas. As I recall, this space is toroidal, meaning the left side, if you go around here, it wraps around to the right side. The top wraps around to the bottom. It's like a donut. If you go on the long side of the donut, you'll get around to the other side. If you go up and around, you'll get around as well. So anyway, a geographically inspired model where we have coupling between different areas. And I've also provided a gridded West Nile virus model where we can have mosquitoes and birds bring vector-borne factors relevant to vector-borne infection spread to neighboring areas. So mosquitoes from one area that are infected can migrate to another area and bring the infection with them. Okay? So geographically situated resources and dynamics are of interest in many cases and provide another motivation for representing space like this, right? A final motivation for representing space like this is more a human factors one than a technical one. Perhaps our model endogenous dynamics don't require detailed consideration of spatial positioning or accumulation processes, or of understanding the exposures to geographically situated influences. But a model such as this, with agents circulating within a recognizable geographic environment, has a curious impact on human psychology that I am at a loss to fully explain. Jeff was the first to note this, as he often is. And what I will tell you is that stakeholders, when they see something they recognize, when they recognize certain features of the model and can relate to them, it often enlivens the discussion, and it gives a sense of credibility of the model, or a sense of model relevance that extends beyond what you might expect. More than that, it will help sometimes ground their understanding that a model is representing things in some concrete world, and that it's kind of mimicking world processes. There's something about the geographic, exposition that allows them to tune into that. And so GIS features from a human standpoint, from a human interface standpoint, human factor standpoint, they play a particularly, and I would almost say peculiar role in sort of alerting us to alerting stakeholders to what we're doing, and helping them clue in to what we're trying to capture. Particularly if you can combine these models with visualization atop of this that uses color, size, geometric cues such as drawn from this palette over here, to sort of highlight things, and from this pictures palette to illustrate things. That will be something which can help enliven a model. And your stakeholder context better than I, but what I will tell you is that my experience with GIS models is that they command attention beyond what you would expect. And in as much as you're seeking attention to get time of day from a policymaker or their policy analysts to really have them understand what you're doing, using this as a way to sort of capture attention, and then go through the substantive features of your model seems to me, a strategy that's worth considering. Jeff, anything you want to utter about geographic models?
I think also just using the idea of sort of a halo around an object, a dot, so you can actually have kind of two different states in a single thing. It's quite efficient.
So you're saying something like go beyond this little thing and put in a sort of an oval around them, which might indicate aspects of their health status, their knowledge, attitudes, or beliefs, the type of behavior in which they are engaged.
So the idea is that the change in fill color represents one.
Yeah.
The change in outline color represents another.
Right.
That's very powerful. So you get
Good.
Kind of multi-dimensional things that are very well. They're just intuitive. You don't have to read the axes on a graph.
Yeah.
We often also say things that are inside you. Things like motivation ought to be in the inner circle, and things that are behavioural and observable should be. So the latent variable is in the middle.
Beautiful.
The outside is the things that people see. But the things that drive you in terms of motivation and intent within the circle.
Right.
We did that for the alcohol model where the size of the circle indicated the blood alcohol concentration. So every time we presented that visual, it really connected with people, and they had a bit of a laugh watching people get really drunk in the pub. So really quite a great way of engaging.
Yeah, that's fantastic comments. Maybe I'll just use that to mention, there's, as so often, I have to triage a lot what I cover. One of the things I did want to cover is if we drag things in there and you want to set the visibility of different items, and particularly their kind of which goes atop what. If you drag that in, you'll want to do order, bring send to back here to place that behind this so it doesn't occlude it. And you'll notice yesterday we had some issue, you may remember, with these not appearing properly. Do you remember that? So I'll actually make this a little bit smaller. There we have this around that. And that issue with them not appearing, that was due to a buzzing feature, but one I've seen before. I'm not quite sure it chose to rear its head at that point. But basically, within the population as a whole, so here, main, notice I'm navigating to certain things over here through this interface, through the projects, rather than always trying to find them in this area. If we go to population and we scroll down here, occasionally I'll be in a situation where you have to basically say show it. It's not actually by default showing. So if you don't see things appearing, if it's a network, go to the connections, make sure that checkbox is ticked for showing the lines. If a person doesn't appear, go to the population and make sure it says show presentation. Now, there's further an issue where there's an ordering shown on the canvas for the multiple populations. And normally, in my experience, that's something you can adjust with several icons here, sending them to back. Here, it seems to have been upstaged by the GIS information for reasons I don't fully understand, and I don't see that option to sort of set the relative positioning. Anyway, those are some comments. Something I should mention, just because we've made very little use of it, is our very first model that I think we built, the first rendition of this model, we actually had people changing color. Do you remember that? We had a color spelled in an appropriate way variable. Remember that? Yeah, perhaps all too well. So, ladies and gentlemen, in order to do that, you may recall that we went to the oval. By the way, it's often easier, in my view, to sort of find the geometric, the kind of presentation properties of these through this menu over here. I have a hard time clicking on them without zooming way in, and so I tend to select things here. If you select things like the oval, you can set its color. Remember, we had to do this thing. We had to set it to a dynamic variable here instead of just using it as a fixed color. We had to press this to sort of say, hey, use color variable. Do you remember that?
Yeah.
We did something like this, color. Yeah. We could do a similar thing for the radius. Okay. And just as color could change over time, so can, in fact, the radius. So we could have, as Joanne said, their characteristics very, very sort of visually here, as their information plays out. So we might, for example, have the radius of their oval depend on something like the log of their, okay, here we go, radius. This is a circle, so we have a radius, depend on the log of 1.0 times their, cumulative years smoked or something like that. Cumulative years smoked till now, right? Something like that. In which case, when we run this, and I'm not actually all suggesting that you do this, but if we run this here, and so we're going to see actually, did I have 0 times? I thought I had 1 time, but okay.
1 times 0.
1 plus, I thought. It was 1, did I do 1 times?
No, you 1 plus 0.0 times.
Oh.
Yeah.
Oh my gosh, okay. Thank you. That's not intended. No, it was 1, it's supposed to be this, okay? Yeah. Thank you. So we're gonna have to start that again, and if we were to do that, we would see aspects. This is probably not gonna, sorry. I just realized we're gonna need to refine that slightly more, because shouldn't be, we're going to need a scaling effect in order to have this be of any size. So maybe 5, 10 times this or something along those, 10.0 times that. And then we're going to have individuals who are smokers for longer periods have a halo whose size is going to be varying, and it's going to be varying dynamically as they are smokers, although in a way that's slow compared to the sort of dynamics that Joanne was talking about, okay? And interestingly, these individuals right now have very low cumulative time smoked, so they are going to have barely visible halos, if at all. And if we went down to population level here, you could see this guy has, now the fox is starting to show its tail. Okay, here there. So this is a serious smoker. I'm sorry. So keep it. For some reason, when I read this, maybe because of my woes in preparing for this trip, I keep thinking this looks like a visa thing stamped on or something. Okay. Anyway, so an illustration here. Here are the big smokers, right? Okay. So let's get rid of this thing which is appearing. How do we get rid of it? These are practical things. Conceptually, not terribly interesting, but conceptual. Basically, you go here and then you basically say this. You don't want it. Okay. And having done that, now it's going to not show that when we run it. We'll be free of that aesthetic blemish. Right? Oh, okay, great. Okay, 2 steps forward, 1 step back. Okay, so now we'll go engage in further frobbing behavior. Okay, so here we go. There we are, and a similar principle. We say we don't want it to appear at the upper level. Right? Here we go. We'll run it. Boom. Now, like many things in any logic, you have many ways to undertake actions, and one of them is which one you use to run a model. You notice I like to right-click on a scenario because then I'm very clear which scenario I'm running. There's 2 other ways in which you can run the model. Model run, and you could pick which scenario to run, or you could use this button, the big green button. Okay, and different parties seem to have different preferences for what's done there. I like this because I could pick very clearly which one to run. Anyway, those are some comments on GIS. Anything else, Jeff, you want to add? Yeah. GIS environment does require network connectivity if you are, unless you're rerunning a canned example you've run before. When you do run it, I'll highlight this. Maybe I'll illustrate this vividly. So let's go to this component here, and I will go down to random number. I'm going to run this as a fixed seed. So every time I should get the same results. Okay? Let's run this thing now. Ooh, did I just? Okay, no. Okay, fine. Now I'm going to run it, and one thing you may notice is when I'm running it, let me just, to make it clear, I'm going to make this fixed seed with a seed of 10. Just so it's a seed I know I've never run in front of you before. Okay? Are we okay with that? A seed of 10. Here we go. Sorry? Oh, did I say 10S? Okay. Sorry. This is very difficult for me because it's not appearing on my screen. So I have to look at the screen there. And normally I use distance glasses when I look at distant screens. Because I'm switching back and forth, it's a challenge. Okay. So ladies and gentlemen, you notice that this is, see this little downwards flowing arrows? This is an indication it's doing some routing. So it absolutely needs network connection right now to do that. It's actually hitting routing servers in addition to loading imagery associated with this, the street map, etc. Now you notice as time goes on, it's going somewhat faster. And in the fullness of time here, it's going to actually stop needing to access this resource because it will have loaded all the information, it'll be remembering it. In computer science terminology, we say that it'll have cached the information. It'll have a little cache where it doesn't need to keep on querying that information. So once it has built up the cache, and I'm going to let it go for a bit, I'm going to go back to this model and rerun it in a minute here. Okay. So here we are, we're about 8 years out, and it's still using some of that information. I'm actually surprised it's still hitting the server here quite that much. Is this one where the population immigration rate? Yeah, you're right. Mumble. Okay, great. So I'll stop immigration here. Okay, no immigration. So I'll copy this. Copy. Boom. And I'll paste it here. And here we go. And then this will say no immigration. Thank you, Jeff. No immigration. I'll turn that to 0. So now what we're going to... Oh, God. Okay, great. Okay. Okay, sorry, folks. it died. Okay, so the basic deal is if we run it with the same seed, no immigration, so we don't need to constantly be adding new locations for things, it's going to be able to reuse the results of the earlier run. And that includes all the information that it's obtained from the routing servers and so on, which actually means that I can rerun it without network access the next time, because it's actually got all the information it needs to do the appropriate routing. Okay, and that will allow it to be distributed in a more flexible fashion. That cached information is quite large in its scope, and as a result, you need to be aware that to pack it up can require some space. So here I'm loading this model in. Hopefully it will be okay. There we are. It lost my new scenario, but that's okay. I'm going to just modify this, copy. Let's make sure that its randomness is set to, here we go, 10. Good. We'll copy here, and this time I'll be more delicate. Okay, here we go. Okay, and 4, save. Get rid of this, 0.0, save. Here we go. Okay. Oh, it's refused to rename that as this. Okay. 04, no immigration. Save. Okay. Great. Okay, run. So now what it should do is it should load in that information up front. Okay. It's looks like it's not even loading it. Maybe it loaded it quickly enough that that it didn't even need that. Or maybe it was because I did run it a little bit. Yeah, it's because I ran it. So I'll change this to 11. Here we go. I did run it prior to it crashing. Okay, so here we go. Okay. Yep, here it's loading down the information. It's going to do that for a minute or two here. I'll keep it up here so you can see it. It's continuing to load. Basically, it's figuring out all the routes between these people that are present. Okay, now it's home free. It's just going forward at a much faster rate. These smokers are exhibiting adverse behavior, and here's a former smoker who's trying to stay quit, right? They are doing so. Okay, the years pass. Oh my gosh, that must be a child. Uh-oh, the child became a smoker too. Uh-oh. Okay. The old man stayed a former smoker, but the child exhibits adverse behavioral imitative behaviors. Yeah, here's another one. Okay, okay, I'm going to stop this. Now I'm going to run it again. Same random, same fixed seed. Here we go. And this time it doesn't even need to go to access the information. It knows about it, so it hits the ground running much quicker. If you go and you look at where these models are stored, here, models. Okay, where are my models? You're there. There's this thing called a cache, and this contains basically the information from the geographic information system. So if you're going to transmit this model to someone who doesn't have a network connection and you'd like them to be able to run it, you're not sure they have a network connection, you can pack it up with the cache and give it to them. Okay, GIS, ladies and gentlemen. But yes? Can you analyze the?
For the routing data, can you actually have a look at all the different routes and then
Good question. I'm not aware of a mechanism for doing that. One thing that you could readily do, and we're going to be talking about this today, is with any logic model now there is packed up a thing called a database. Do you see that? And that database provides a way of easily storing away information for export over time. So if I were you and I wanted to maintain this route information, I would put it in there. The cache, what any logic stores, you don't want to be, almost by definition, a cache is a convenience, and it can be thrown away if it gets too big or something, and you wouldn't want to count on it to maintain the information. Okay, you'd want to put it into probably a database. Okay. Other questions on GIS? Yes.
I'm
Robert.
thinking can you use two time parameters? For example, I'm interested in the time people spend in the hospital.
Mm-hmm.
And that would be in hours probably.
Mm-hmm.
Whereas the rest of the project moves in years.
Yeah,
as
yeah.
I want to see the whole
Sure.
trajectory of
Yeah,
life.
yeah.
Is it possible?
Absolutely, yeah. And I'll draw a distinction between what you see here and so I'm gonna comment in response to your question actually at two levels. So at a broad level, is that possible? Absolutely. The agent-based models that we've been running, in fact, discrete event simulation models too, like this one we have here with the clinic, right? Where we have this clinic. These don't run according to a fixed schedule. What I mean by that is things happen as quickly as they need to, or as slowly as they need to. So you may have a situation with sort of a punctuated equilibrium where things are happening very slowly in general. You know, it's kind of in a sort of stasis, and then something big happens, and there's an outbreak, or there's a public health crisis around some issue, or a person comes into the hospital and needs to be stabilized. Where things happen very quickly, a stroke happens, and every minute counts to getting them in under care. And the scenario, the scheduling that's supported here, any logic is basically a big part of any logic's functionality comes from the fact that it's this event schedule, okay? In other words, it maintains, as one runs this model, a schedule of events. It basically has a queue of events that it is processing behind the scenes. It goes from event to event to an event. What are these events? Well, an event might be a person ceasing smoking or relapsing into smoking. It might be someone engaging in initiation or someone developing heart disease. It might be a delivery of a baby. It might be a recalculation of the fertility rate. Many other things here can be reduced to events. Even things that are dynamic, like you can't pre-schedule, things like this message, that's an event that needs to be scheduled, okay? And any logic has the schedule of events which need to be handled, okay? And it goes from event to event, with each event something needing to happen. Maybe it schedules another event, or it runs some code, so they arrive at this location, that's an event, and it runs this code to take them into the clinic, right? These are events, and any logic has this event schedule, and the event schedule could be as fine temporally or coarse temporally as is needed to run the simulation. So if things happen in really quick succession, that's no problem. If things don't have to happen for a year, that's no problem at all. It'll just go forward to the next year. And that's a big difference from system dynamics models, where with system dynamics models, you are actually evaluating things on a certain time scale. So this, do you remember this? Here's the predator-prey system IMX model here. Do you remember this model? So in this context, what we have is this model is integrated with a certain time step. It's actually run forward a little bit of time on turn, and so every time step it's calculating the flows, and it's updating the values of stocks based on the inflow and outflow. Okay, and that's updating those values, and so this is going through at a very regular time step. Okay. And there's methods like Runga-Kutta which allow you to do it with not quite uniform time steps. But basically, this is a model that involves kind of a lockstep evaluation of this with fixed time steps. So if you have a system dynamics model as part of system dynamics component as part of your model, it's going to need to be sort of updated on a very, very defined time step. But the rest of the model can go broad amounts of time forward. And this is in contrast, there's actually a fair number of agent-based packages out there where you require a fixed time step. That's actually been the norm. In fact, I've heard a prominent colleague of mine even opine that agent-based modeling must have a fixed time step. That's part of its definition, which I think is completely off base. But the point is, traditionally, agent-based models have used these fixed ticks. And one of the big problems with that, if you don't have continuous time, if you don't have things happening at their natural times, but it's a fixed tick, is then you've got an issue with, thank you, Joanne, then you've got an issue with the fact that you have to figure out for the past tick, say month or year, which of several events that might happen during that tick happened first. Because you've got to figure out, do I count this as being a cancer case occurring before death, or did they die in the past year before they developed cancer? That sounds strange, but thanks so much. And a model like what we have here, thanks enormously, Joanne. Testing. And a model like we have here, where we have all these different types of actions, there's a very real thing, right? Did someone deliver a baby before dying, right? That's a very real issue. Did someone develop heart disease before quitting smoking? If you have things divided up into fixed time steps, suddenly you're doing this work to kind of manually broker which occurred first, which occurred later, and it ends up leading to kind of complicated and fragile logic, because people have studied these things and found that if you do it in a different order, sometimes it makes a difference, and really it's a great strength of any logic, I think, as a platform. And it's not the only agent-based platform that does this. ModGen is another one in the microsimulation area that uses continuous time. It's actually a real asset. It simplifies our thinking. Things happen in a natural order, the order that they happen in the world, and as fine time steps as needed or as coarse time steps. We don't have to say, well, because during a crisis things may have to happen at the level of a minute, that now the entire simulation has to be articulated at the level of a minute. That leads to very poor performance. And so we can avoid that with this sort of context. But it becomes more tricky once you have a system dynamics module as part of this. We're working to try to lessen the burdens there, but they're right now in any logic, they're pretty significant. Okay, thanks. Any other questions about this? Okay, so this GIS was a big part of what we did yesterday, but it wasn't the only part. We also had other features. We created, ladies and gentlemen, a hybrid model. It's a hybrid model. We have persons and we have clinics. The persons present to clinics. The persons, their dynamics are characterized using traditional agent-based mechanisms, state charts. clinics, their dynamics are characterized using what? Discrete event. That's discrete event modeling. We didn't really speak to the strengths of that yesterday. But a lot of the reasons we use discrete event here is because not only does it provide a very nice way of describing a workflow process, but allows us to ask questions, really easily investigate questions like how would changing the number of clinicians change the fraction of people who leave without being seen? How would it reduce the time from start to finish? How would it increase the throughput of the system? How many people can be seen per day? We didn't really have a chance to explore those, but just to give you a sense of how finely honed this sort of modeling is to investigating some features, let me show you one thing. A thing without showing which I'd be, without which, if I neglected to show it, I would be negligent. Okay, ladies and gentlemen, let us repair to the palette. And in the palette, let us seek the company of the process modeling library. No, Annie's going to have to get ready here. For the process modeling library, I would like for you to draw into here a mechanism from the palette that's basically going to allow us to easily measure, okay, this is really annoying. It's basically going to allow us to easily measure how long things take. There should be something in here that is called time measure start and time measure finish. I can't read what this says, so I'm going to put on my distance glasses here.
Down towards the bottom.
It's, yeah, that's what I figured. Is it here? Is this it? Here? Okay, yeah. Okay. So, ladies and gentlemen, I'm going to drag in a time measure start here and splice it in here, okay? Boom.
Is that before the wait for clinician or in the process?
It's a good question. I mean, I could do it at either place. Basically, you can use these things to measure time from an arbitrary point to an arbitrary point. Maybe what I'll do is, per Roberto's suggestion though, maybe I'll put it out here rather than putting it there, okay? Maybe we'd be more interested in including these features here for the entire time. So I'm going to do time measure start, and we'll splice it in here, okay? You ready? Time measure start, and we could call it time measure start. And then finally, I'm going to need to, one challenge of doing it there is I actually need the next component of it to be, it needs to be capped by another one. And I can't easily put it on here. What I can do is, I think I should be able to just do time measure end here. Okay, I'll splice it in there. And I'll do time measure end leave without being seen, LWBS. And I'll do it here as well. Time measure end. And this is standard flow. Okay? Now, for each of those time measure end, each of those time measure ends, we're going to need to indicate what is the corresponding time measure start block from which we wish to measure this. okay? So here, for the top one, or for this one here, I'll do a plus and I'll pick that. Same thing for the other one. I'll do a plus. Okay, and I'll pick this.
Is that in minutes, seconds, hours?
The time units of the model,
Mm.
which are years here, right? So it's going to be measuring time. We could always convert from one time unit to another. So here, ladies and gentlemen, we have a way of recording times from one endpoint to another, or one point to another. And by running this model, we can develop statistics about the variability of those time measurements. Okay? And if we go down and we look at a particular clinic, for example, here, I'm going to be running this. So see with this, people are coming in here. You'll notice that this time measure, if I go click on it, it'll report for me a maximum time, a minimum time, and a mean time. This is all in years. And this gives the standard deviation concerning that. Okay. Meanwhile, this time measure end, we haven't had anyone balking yet, so they haven't gone in that direction. Okay. So this provides this way of sort of getting statistics on latency, how long it takes them to get through the system. And with discrete event modeling, we can engage in that sort of measurement very easily. We could ask, how does it change as we change the number of clinicians, right? Okay. So discrete event modeling was a key component of this. And as you could see from the palette, there's a wide variety of other components of discrete event modeling. Some of them are more directly relevant to the interests here. For example, service blocks are very useful. They kind of combine features of queues with features of seizes. If you're having a facility where you have physical layout of the facility, you could use move to blocks, which will basically allow you to move an entity to a certain location. You could have a resource send to, which will move a resource like a doctor or a portable, a doctor with agency to a certain location. And then there's some that are less relevant. There are things that handle bulk materials, conveyors that will take things down, etc. But this sort of modeling is very versatile. When we wanted to create a hybrid with this, thank you so much. You may recall there were basically two major nexi that were featured. One is when the person needed to be taken in to this model, to this discrete event model, through this walk-in.take. This is where they got placed in the model. They didn't leave being an agent. They were still an agent, but they also joined this workflow. Okay? A second major nexus was associated with when we influenced their behavior or state over in the agent-based model area. And for this person who was in this area, we influenced their behavior or state, such as moving them from a not motivated state to a motivated state, by sending them a message. Okay? So in this workup, we sent them a message by which they were diagnosed or might be diagnosed, and by which they were motivated. that method for diagnosis might be successful or it might be missed. And for a patient, they might similarly get motivated or not, according to their history, according to their characteristics. They might or might not be motivated. But this is where we basically the discrete event modeling came together with the agent-based modeling to change the state of the agent-based model. And generally, that's what we want, right? We want a service facility that serves the population. People present for care. The features of that service facility, how many clinicians it has aboard, its resource availability, its location, these things will affect care-seeking behavior. We have some models which look at trust, for example, and the way in which trust shapes care-seeking. But another side of that is the service delivery affects health status. And particularly when it comes to things like self-care, when it comes to things like motivation, trust, diagnosis, the service delivery is pretty darn important. And rather than having these be solitudes, two different worlds of service delivery and public health, which don't speak, this provides us with a ready way of having them come together and having them affect each other. The population health affects the load in the clinic and its characteristics, its quality level, and its ability to provide care in a timely fashion, to inspire trust, ends up affecting the population health. And that's what we can readily represent using these hybrid models, just as we did yesterday. Care seeking, care delivery, and ongoing evolution of a person's health state. Not to be trivialized. It's rare that models have ever brought both under the same roof. Here, it's a quite straightforward matter to do so. Okay, I think I'll leave my retrospective comments on that. Any questions from yesterday before we go on to new material? No? Okay, great. So I'll stop the recording here.